Hello, everyone. Today we're going to discuss about a data structure called tree. As you know, data structures are used to store data in an organized fashion. And a tree is one such data structure which also stores data in an organized fashion. Let's look at a real life example where tree is very handy. So let's look at this organizational chart. Let's say this is an organizational chart. So this is actually an example of a tree. I will show you a little bit more. So let's say this is the CEO of the company. His direct reports are the president of the company and the CTO of the company. Now the president has a few vice presidents reporting to him, and the CTO has uh, he has this also some managers, let's say some technical managers reporting to him. Okay. And these managers also may have employees under them, their own direct reports. Okay. Suppose VP also has someone under, two of them under him. So to store this kind of information, the data structure that comes most handy is a tree. Now let's see how tree data structure is formed. So first of all, these are the nodes. So these are the nodes. Okay. So nodes are, and each node has some data. For example, here, each of the nodes has, the first node, say this node has data about the CEO, right? How many years he's working, his expertise, a lot of other information. This node has data about the president, right? This node has data about a particular VP. So each node has some data. And then the next thing that comes is edges. So node, trees consist of node and edges. So edge means the links or connections. So each node is actually linked. So this is one edge. This is one edge. This is another edge. This is another edge. This is another edge, right? So each node may have links or connections to multiple other nodes. Suppose the CEO has links to two other nodes. The CTO has links to three nodes, right? And each of these links are called edges. Okay, so let's move on to see. And from here, you can see that tree data structure is different than the other data structures we had studied before, like arrays or linked list, right? Linked list or stack or queue. These were like all linear data structure, right? These were linear data structure, whereas tree is a hierarchical data structure. You can see in the picture that what a hierarchical data structure means, right? Okay, so next, let's familiarize ourselves to some terminologies. First of all, the node at the top, the node that is at the top is called, so this is the node at the top, right? This is called the root. Okay. So this is the root. And then we already know about the edges, right? Edge is the link or connection between two nodes. Now we said that any node can have, say, any node can have links to multiple other nodes. So suppose this node L has links to multiple other nodes. So L has connection to, or it has edges to E, F, and G. In that case, we can say L has links to its children. So a node may have link to one or more nodes, which we call the children. So here, L is the parent, and E, F, and G are the children. Okay. Similarly, if Q is the parent, then A and B are the children. Okay. Okay, then if two of the nodes have the same parent, say A and B, they have the same parent, right? Then we call them siblings. So okay, now if I ask like if B and C are the siblings, No, because C has a parent R and B has parent Q. So they have different parents. So they're not siblings. Then let's talk about the leaf nodes. The leaf nodes are the nodes that don't have any children. So here you see, suppose B. Is B a leaf node? Yes, because B doesn't have any children, right? So B is a leaf node. Similarly, you can see H, I, they are also leaf nodes. And as well as E, F, G, these are also leaf nodes. So leaf nodes are the nodes that doesn't have any children. Now, the next one, let's say ancestor. As the name suggests, ancestors are all the nodes that come before that node. So suppose for B, what are the ancestors of B? If I say ancestor of B, what are the? Obviously, Q is one of them, right? Because Q is the parent of B, and then P is also ancestor. So the answer is P and Q. These are the ancestors of B, right? So the parent and then the parent of the parent, then parent of the parent, those are the ancestors. Similarly, if I say descendants, so what are the descendants of, say, A? So descendant means obviously L is the child of A. So L is the child of A. So A is a descendant. Again, L has its own children, E, F, and G. They are also descendants of A, right? Okay. Okay. Now let's talk about two very important terminologies. So those terminologies are the depth and the height. So if I say depth of node, say C, so the depth is calculated by the number of edges from the root to that node. So you see for C, how many edges are there to the root? So 1 and 2, right? So we can say that the depth of node C is 2. Okay. Okay. And then if I say, let's say, what is the depth of G? Okay, so how many edges are there from G to the root? 1, 2, 3, 4, right? The depth of G is 4. Okay, so there goes the depth. Next is height. Now, sometimes we actually make the mistake. We think the height and the depth are the same. That's not true. So height means the number of edges in the longest path from that node to the leaf. So if I say height of C, What is the height of C? Okay, in that case, the height of C is going to be, I have to get the longest path, 1, 2. And H is a leaf node, so height of C is 2. And if I ask you, what is the height of, say, Q? Okay. Now, Q has a distance like there one edge. We know that B is a leaf. So the number of edges between Q and the leaf node is 1 if I consider B, but that's not the height of Q because we have a longer path, right? So I have to take the longest path. So if I go to A, then L, then say E, then you see that I have like a path of length 3. So the height of Q is 3. Okay, so there goes the height. So these terminologies are going to be important when we actually will discuss about trees. Okay, so in the example here, you see that the tree may have like any node may have any number of children, right? Now let's talk about a specific type of tree where there's a constraint. So this is called binary tree. So this is a tree, but the constraint is each node can have a maximum 2 children. That's why this is binary. So you see that any node here can have maximum of 2 children. Now, this node 4 doesn't have like, it has 0 children. That is fine. Or you see node 9. Oh, sorry. Node 9 has 1 children, right? That is fine, but you can have like 0 or 1 children, but not more than 2. You see, none of the nodes have more than 2 children. That's why we call it a binary tree. And the problems, most of the problems that we will be talking or the problems that we are going to solving are related to binary tree. Okay, so let's move on. And some of the, sorry, some of the use cases, real life use cases of tree. So first of all, storing hierarchical data or hierarchical data. For example, the company employee diagram, right? The first example that I showed you, where, okay, and then there is, trees can be used to organize data. Suppose one such example is binary search tree. We're not going to details for this in this lecture, but binary search tree, we are going to discuss details soon. This is used to make searches easier, searches efficient, I would say. Okay, so binary search tree is also a kind of tree. Obviously, this is a binary tree, you understand, and it has even more constraints. So it's a binary search tree. And finally, some other data structures, say trie. We'll also discuss about these data structure. Trie is also a special kind of tree, and this is used to create dictionaries, like word dictionaries. So that's all for, we discussed the logical model of tree. That's all for today. And in the next lecture, we are going to talk about the binary tree.